So we're going to have another look at the falling magnet because it's a bit of a classic, crops up in questions quite a lot. So well, we already got some kind of idea. We know that if I plot flux linkage on the y-axis and time on the x-axis, well, we know this is going to start off like this. It's falling towards the thing. We'll assume it's a long way away at the beginning, so effectively there's no flux linkage, right at the start, it's high up. But as it gets closer, the flux linkage is going to increase at an increasing rate. One, because it's going faster, and two, because the field lines get denser as the magnet approaches. So we're going to get a shape like that, and then of course it's going to fall out the other side and disappear. So then the flux linkage is going to decrease, and it's going to do so in a similar kind of way because the density of the lines kind of diminishes. So we can expect a kind of curve, something like this. It's going even faster now, so we expect that to be even steeper on the other side. So I hope that makes sense. Well, what we're of course interested in because of Faraday's and Lenz's law is the induced EMF. So on this graph, that's exactly what we're going to plot. So induced EMF and against time. Well, all we have to remember, or I say all, but the main thing we have to remember is the law itself, which is that the induced EMF is proportional to the rate of change of flux. So minus dn phi by dt. So that, well, that of course is minus the gradient of this line. So we can actually plot that on the other graph. We can see that the gradient is initially 0 there. We've got a sort of point in the middle, haven't we, here, where there's a kind of peak. So that means that that has a 0 gradient there. So we know it's got to go through a point in the middle of the graph just around here. And then also the rate of change diminishes off to 0 again, sort of at the end of the curve, because as it gets far away, those field lines, there's very gradual change in the almost 0 field now. So we've got to kind of conclude what the graph's going to go through those 3 points, but what will it look like on the way? Well, you might want to have a go at a sketch. Hopefully you discover that, well, the gradient of this is getting bigger, and then very rapidly goes to 0. So, well, we need to go negative in this case because it's of the minus sign. Now you do sometimes see the question with this as a positive because it's fairly arbitrary, but to be technically correct, we ought to have our minus sign. But you can see this in either direction, but we're going to do it in the negative direction. So the voltage is going to go something like this, it's going to build up, and then it very rapidly diminishes down to 0. And then on this side, well, the gradient is going to go very negative and big, and then back to 0 again. So, and of course that means that we've got minus the negative, so it's going to go positive. So, and it's steeper. This side, because it's going faster, is actually more steep. There's a bigger rate of change, so there's bigger induced EMF on its way out to the other side than there is on its way in. So the peak is going to be a bit higher. So a very rapid rise, and then a sort of diminishing away like that. So that's the shape of the curve. A couple of points to make here are that we've got some very interesting features. First of all, the first peak is lower than the second. And what I mean by that is the first peak has a smaller height, it's a smaller magnitude of EMF than the second peak. But we've already decided that's due to the steepness of the curve. It's going faster, basically, the magnet on its way out than on its way in. Second point to comment on is that the first peak is wider. Now, why should that be? Well, you can actually use the same argument here because I'll just show you on the graph there that what we're saying is the time of delta t of the first peak is bigger than for the second peak. But I mean, the same argument applies that it's going faster in the second or slower in the first peak. And there's another reason for that as well, which I'll come on to now, because there's an interesting thing which isn't obvious, but the areas of both peaks are equal. Well, why should that be? Well, the answer is that if we look at our equation here, well, the change in flux, or minus the change in flux, is equal to the EMF multiplied by the change in time. Well, that's for each little infinitesimal bit of that graph. But what it does mean is that hopefully you can see that it's going to be the area under the graph. If I sum up all those little elements to get the total change in phi, then the total change in flux will be the area under the graph. And therefore, well, the amount of flux entering must be the amount of flux leaving. This magnet is going to completely go through the coil, so as much flux must go in as goes out at the end. So in other words, these two areas are actually equal. So that's kind of a nice little bit of physics there.